Okay. Okay, so. In terms of Washington boards, we don't got all the boards today. Anyhow, domain and range for each of these functions. You can't divide by zero. So x minus 7 cannot be equal to 0. Now you solve this for x. Okay, we add 7 to both sides. All right, 7 equals 7. I'm adding 7 to both sides, I get x is not equal to 7. Okay. If this isn't equal to this, then 7 more than this is not going to be equal to 7 more than this, right? Okay. So we could actually add to both sides of an inequality. Or we could solve for when x equals 0 and say, well, it can't be. Okay. One way or another. So the domain is all values of x that aren't 0. The way open math would want you to express the domain is as a union of two intervals. Okay. Now, do we understand what the intervals mean? 0 infinity means all the numbers from 0. I'm sorry, negative infinity 0 stands for all the numbers from negative infinity up to 0, but not including 0. And we can sketch those. Here's 0. And so the domain consists of all the numbers to the left of 0 and all the numbers to the right of 0. So the interval negative 0 infinity is here. The interval 0 infinity is here, but 0 isn't included, so we put an open circle around it. Everybody seen that at some point in their education? Well, lock it in now. Okay, if it isn't already locked in, but I'm sure it is for many of you. Okay. Now that's the only restriction. Okay, because for right now, almost everything you see is going to involve square roots or division by 0. So you check these two things out. There's more, but if you can just check those two things out, it's a good start. Okay. Now the range is a little more complicated. So I'm not going to talk right now about the range of this function. Okay. That's something you're going to maybe have to dig out a little bit. But I'll do an example. But for right now, I'm going to keep it as simple as I can. Okay. You got g of x is a square root of x plus 2. This principle here, division by 0. I mean, the square root of a negative isn't defined. Over here we can see it. Okay. Restrict the domain they have here. Like, for example, if x equals 20, you got the square root of 22. That's fine. You don't know how to calculate. Your calculator will give you a very good approximation. Okay. If x equals 23, then that's a square root of 25, because you know how to calculate that. If x equals negative 10, you got the square root of negative 8. Well, the square root of a negative number isn't defined because the square root is a number you multiply by itself. You get the number you're looking for. Okay, and there's no number you can multiply by itself to get a negative. Because if you multiply two positives, you get a positive. If you multiply two negatives, you get a positive. You can't get a negative number by multiplying two numbers, so there's no square root, no real square root of a negative. They're complex square roots, you'll see that later, but right now we're doing real valued functions. So we have to say then that x plus 2 is greater than or equal to 0. Well, we can solve that. We can take u equals 2 and add it to this inequality, -2, is -2, and add it to this inequality. It won't change the truth of the inequality. Okay? If this is greater than this, then 2 less than this is greater than 2 less than this. We get x is greater than or equal to -2. It's that simple. We write down whatever's inside the parentheses and say it has to be greater than or equal to 0. Then we can graph it. With 2's here in the number line. And we've got everything from here to forever. And we include the 2. So to be clear, we put a big old dot on the 2. I wrote it bigger than we really have to, but I want to make sure everybody sees it. Okay. Okay, now. After these two examples, see if we can write out for this. I'm only going to give you a minute or two. See if you can write out what restrictions there might be on that. There might be more than one. Okay. For this function, what's the restriction? The 2 things to look at. You got to write those down someplace. And remind yourself that when you look at an expression, you got to look for division by 0, and you got to look for negatives under the square root. Okay, comes down to that. So I was going to say, because I've written it out here, the x minus 3 can't be negative, right? So x minus 3 has to be greater than or equal to 0. So you add 3. And you get x greater than or equal to 3. Okay, so x has to be greater than or equal to 3. And also x plus 5 can't be 0. Well, subtract 5. Adding the equation, -5 equals -5. And I get x can't be equal to -5. And that's common sense. If x is equal to -5, you're dividing by 0. Okay. If x isn't greater than or equal to 3, this is negative, and you can't do the square root. So simply write down these inequalities or non-equalities automatically. Okay. And you say that, okay. At some point, somewhat, say the remains all values of x that are greater or equal to 3 and not equal to 5, right? Not equal to -5. Well, this really doesn't matter because that has to be greater or equal to 3. It isn't going to be -5. Okay, so you could do the number line. You could say, okay, here's 3. And over here is -5. So it can't be -5. Can be 3. Or anything greater than 3. Since it has to be greater than 3, it doesn't matter that it can't be equal to 5. So this is saying can't be -5. But we ought to know that. It doesn't add anything. Doesn't hurt to have it there. As long as you don't put a closed dot on it. If there's a closed dot, that means -5 would be. -5 can't be. That would screw up the square root. Okay. I have to ask, have we done the thing in here where we shade the intervals of the x-axis and shade the intervals of the y-axis corresponding values? Okay, do that. Not everybody's done that for a minute or two. Do what you did, but do it for everyone. No points to go down here. All the points are going here. Go here. You gotta be careful how you do that. You got the right idea. We'll fix that. We go find the chalk. Okay. Okay, so we wanted to change these intervals. Okay. So I take points. That's exactly how I explained it before. If you haven't looked at the videos and haven't reviewed them, I really shouldn't have to take time to explain this. Okay, takes time away from other things I can do to help you. So get on top of the videos if you miss class. Okay, do it systematically. Sometimes that's not possible. But well, we'll do the same thing here. We just project all these points up to the x-axis. And now we see that over here, they start here and they end here. So that everything, we color, everything between here and here is included. I kind of left it ambiguous. I didn't put any kind of a circle on the ends of these intervals. So let me go ahead and do that. Let me put a closed circle here and an open circle here, meaning that everything up to this point is in the domain and that point is in the domain, right? Or that point is a point on the graph, okay? If this is a point on the graph, then this point has to be in the domain. Okay, and this point should be directly below this. Off to the side, I'm not sure if I look at it, that I know that you're seeing it right. It's a little bit one way or the other, yeah. Can't help that, but make it as straight as you can. And over here, I put a big old open circle because this point is not on the graph. So that this last point here will not be in the interval. Okay. Now, it will not be in the domain. So over here, I'll put closed dots in both of these. So that I see that this point is included. And this point here is included in the domain, and every point in between. So there's my domain. Now, if you got your numbers for this point here, this is the point that we marked. Then you know what the number is here, and you can estimate what the other numbers would be. First thing we did earlier this morning. Okay. Then we project all these points over here. Then we project all these points over here. I'm doing a very good job of keeping the line straight. That's the idea. And we see that this point up here projects to here, and that point is included because that point is on the graph. I don't need a dot or anything to show that point's in the graph. So this dot really doesn't matter because we've already got values over here that match these values. Okay, down here, maybe it does, maybe this is the low point. We've got this interval, and up here, we've got this interval. It goes all the way down to those are two intervals. Okay. Okay, now what some of these things mean is one question, and it's really hard to figure out what it means for our book. Okay, I have trouble. I don't know what that means. Okay. And I wish I get that dang tune out of my head, but I can't. It's been with me forever. Okay, so anyhow, without worrying about what any of this means, this is just clarity. F of 3, well, if f of x equals x squared, then if I write f of 3, that means x equals 3. Right? I mean, it's f of x. So if I write f of 3, x is 3. This is the definition of the function. And this is the application. So f of 3 would be 3 squared. Now you can say that's equal to 9. If you do, you're right. I'm never going to write that down. I'm just interested in the clerical aspect of it. Okay. Now, after we do the clerical aspect, then we'll see what some of this leads to. Okay. F of aardvark doesn't lead to anything except a strange looking expression. What about f of a plus b? Well, now x is a plus b, right? Because we've replaced x by a plus b. That means this x has to be a plus b. And of course, x is squared, so the whole a plus b has to be squared. Okay. We don't write out what we think a plus b squared is yet. We just write it out. Okay. It's the first step, and it's a step that people have trouble getting by. So we want to be very careful just to write out the step. No, I didn't leave myself room to write aardvark squared here, but I'm going to do it anyway. That's just a tiny aardvark, but you can still square it. Okay. And you can put parentheses around it or not. If we understand that aardvark is just a symbol, it looks like a word. And then we can say, okay, let aardvark equal 7. 7's not like any aardvark I've ever seen. Okay. We could use aardvark as a variable if we wanted to. Hopefully we wouldn't. What about f of g of x? Well, x has been replaced by g of x. So we replace x by g of x. Right. That's it. Okay. Well, that's not really not it, but that's the step. Okay. What this means, talk about it if we've got time, but we're doing the mechanics. Okay. Now there is a little algebra here, and you got to start looking at some algebra, and you want to understand this algebra. Okay. Now, that's the end. Of the clerical phase, at least for most of these. Okay. We could also write just what we've already got. F of 3 is 3 squared, and now we can do the arithmetic. Some of you already know that 3 squared is 9. Oh yeah, everybody knows that. Okay. I think everybody wrote that down. So that was good. You understand something about function notation. Okay. If you'd had 9 there, You're understanding something. And you understood that X is going to be 3. Whether you wrote it out clearly or not, you understood it. Now you want to write it out clearly because it can get complicated. You want to always write it out the same way until you get to the point where you can skip steps, if ever. Okay. You might never get to that point. Okay, now what's quantity A plus B squared? If you say it's A squared plus B squared, you're wrong. There's no distributive law. There's a distributive law of multiplication over addition. Okay, if you have 2 times the quantity 3 plus 4, that's 2 times 3 plus 2 times 4. That's a distributive law. Or 3 plus 4 times 2. 4 times 2 plus 3 times 2. Okay, and I assume everybody's familiar with that. This looks like there ought to be a distributive law. You ought to be able to distribute the 2 over that addition. Even though it's a square, it's not a multiplication. Well, no, there's no distributive law of exponentiation over addition. What this is equal to is A plus B times A plus B. And that's equal to A plus B times A plus A plus B times B. That's the distributive law of multiplication over addition. You multiply A plus B by A plus B. You multiply A by A plus B, and then you add that to B times A plus B. Kind of seems in reverse order, but that doesn't matter, no. This is elementary algebra, okay? Simple distributor, not simple, it's not the simplest application. And there are symbols, but I've got to assume that if you don't understand this, you're going to take another close look at the video, or you're going to go out and find videos that make it clear, or you're going to look back at the MDE stuff, or whatever, or you're going to email me and say, what should I look at? And another thing you want to look at is the mark, because we've got a really good math tutor over there. Okay. So you got A plus B times A. Well, that's another distributive law. You multiply A plus B by A, so that's A times A. Plus B times A. And then here you got A times B and B times B. A times A is A squared. B times A is the same as A times B. So you got A times B here and here, so you got 2 of them. You got 2 A times B, and B times B is B squared. And this is very different than A squared plus B squared. Okay, so you got to be careful about that. That's a little algebra blurb. Make sure you understand this. I've still got people in 3rd semester calculus 3, that's beyond your comprehension until, beyond anybody's comprehension, until they've had at least a year of calculus. Okay, it's very complicated stuff. So they're doing high level math, but I still see this mistake in some of their work. We don't want people to come out of algebra classes making that mistake. We certainly don't want to come out of pre-calculus classes making that mistake, especially if they have a calculus course in the future, which most people in this course do. Okay, at least an applied calculus. Okay, anyhow, there it is. Okay, now let's look at this f of g of x. This is where we're really heading with composite functions. We've established that f of g of x equals g of x squared, right? Now, y'all did pretty well with that, okay? Most of you got that. And I think everybody understands it now, hopefully. Now, suppose g of x equals 1 over x. What's the expression for f of g of x? Write down what you think it might be. Okay. So the question is, if g of x equals 1 over x, what's the expression for f of g of x? Well, we could write again. This because we've already determined that for our f of x function. Okay, so there's no f here. F be gone. Okay, not there anymore. So we got g of x squared. If people still want to do something with f after we get to this stage, I don't know that. F was here, f had the instruction for getting this. Okay. So what do? Well, we just said g of x equals 1 over x, right? We do the simplest possible thing. It's got to be right. If g of x equals this, we can write this as 1 over x squared. Okay. And that's enough, but you probably want to simplify that. And that's one of our basic functions. Okay. I'm not sure, you probably haven't had the assignment on the 5 basic functions. 1 over x is one of them, right? And we did that assignment in MDE 61, so we're trying to get people a little ahead in that course with slightly easier problems. But you could certainly make a table for this thing using -2, -1, -1/2, 0, 1/2, 1, and 2. Have to exclude 0 because you can't divide by 0, right? Then you make a graph. It look a whole lot like the 1 over x graph, except you're squaring all your numbers, so everything's positive. And some of the numbers are a little bigger and some of the numbers are a little smaller. Okay. In other words, you could sit there right now and make a table for this and a graph. Okay. Well, that's beside the point, but I wanted to point out that that is one of your basic functions, very closely related to ones that you understand. Okay. What's the domain of this function? Okay, so what do we have here? First of all, people didn't have any trouble writing this out. Somebody had a little trouble, but not too much. Okay. Once you get this, this, and this, that's not hard to write. Now, if you have additional information, you have a formula for g of x. Well, you can replace the expression g of x by that formula, which is all we did here. Okay. Now, when you get that, there might be some restrictions on the domain. There's no restriction on the domain of x squared. You can square any number, 0 or any positive or negative number. You can multiply it by itself and get a number, a real number. Works. As soon as you do the 1 over x, then it's going to get a 1 over x squared. Well, you got to exclude anything that makes g of x 0. To do f of g of x can't be 0. Okay. So we see clearly that 0 is not in the domain of this thing. Also, I'll show you what the graph of 1/x is going to look like. It's just like the graph of 1/x, except it's somewhat steeper. Okay. Steeper here and less steep here. But it looks like this. And if I just do the domain of what I've drawn here, here's the y-axis. Okay, here is the domain of what I've drawn. You notice there's a hole in the domain here. Okay. Well, if we extend the domain past the basic values, we close up this interval here and we close up this interval here. But we never have a value for x equals 0. So if we just do the whole function, it never includes 0. Okay, we can include numbers close and close to 0. We only go from 1/2 to 2 here and -2 to -1/2 here for the basic function. But we understand that, okay, we went to 1/2 here, we can go to 1/4, 1/8, 1/16, 1/100000th. Okay, so you get really big numbers up here. But we're never going to be able to use 0. Okay. That's what I'm telling you. And that's the whole idea of domain. I haven't even talked about range. So you're going to have to kind of take that out. But after you've worked on it, we can then address it. Okay. Okay, we're seeing a bit of a deficiency here. It's not unexpected given all the COVID ramifications. I got to tell you, you should be able to quickly construct a graph in polar coordinates and understand it, even set up integrals in polar coordinates, which I'm pretty sure is done in our calculus class. Okay. So if you haven't, I think it's worth an afternoon to review all that. Make sure you're up to speed. Because we're moving into cylindrical and spherical coordinates. And a little later, you're going to have to set up intervals in those things. Okay. And it's going to be an insurmountable problem if you don't at least understand how to set up intervals in rectangular and polar coordinates. Okay. And it's not that you can't do it. You might have forgotten, you're a little uncertain whether you did this in calculus. Pretty sure you would have. Be surprised. Very surprised. Okay, anyhow. Okay, you got r equals cosine theta. Now we've got to do this quickly. We're going to graph the polar coordinates. We want to start out with your probably 6 angles or 3 angles through the quadrants. In other words, angles in multiples of pi over 6. So here you've got pi over 6, pi over 3, pi over 2, etc. You know what this is about. And everybody want to tell me what this is can show you what's it saying? What you want to see. Okay. Okay. Okay, so we can make a table. And you know, for a lot of these functions, you kind of do want to make a table. Well, R versus theta. What kind of theta? The theta is an independent variable. Now just go from 0 to pi over 2, because once we see what happens there, it's pretty clear what happens everywhere else. Okay. Everybody should know that your cosine of pi over 3 is square root of 3 over 2. Be able to derive that by drawing the triangle, cut an equilateral triangle in half, get the dimensions at the sides, 2 of the sides, you get the third side, and you get the cosine. Very simple. So we've got this much. So let's just take this much information. If theta is 0, r is 1. So r equals 1 here. You do a backward length 1 and 1 up to this point. R is 0.7 along the 5/6 line, so that's going to be a little less. It's going to be 1 so. R is equal to 1/2. When you get out to here, it's going to be about half as long. You have a point here. And then somehow it comes all the way around to 0 here. Well, if you do this, and I said 0.7, like 0.87. That's a little longer than what I have here. So it's going to end up making a semicircle here. You prove it as a semicircle, and I'm not going to show you how to prove it's a semicircle. You should be able to prove that after you do a good review. Okay. Then what happens? The values of the cosine become negative. So if we come out along the pi over 2 pi over 3 line, we have a negative on. R is going to be negative 0.5. So for pi over 3, we go negative 0.5. We go here. So this is okay, that's 2 mistakes. Write it out correctly. Okay, R is negative 1/2. Pi over 3 is in this direction. 2 pi over 3 is in this direction. Okay. So negative 1/2 in this direction is in this direction. So there it is. Okay. Well, you're going to follow the same values around here, and you're going to end up with theta is pi. You're going to get -1 for the cosine. So you go up pi direction, -1 unit, you're going to get it up right here. And you got circle. Circle radius 1/2. Center, if you're on the x-axis, it'd be 1/2 0. Okay. There it is. Now you do get like cloverleaf shapes out of this. If you did r equals cosine of 2 theta. Okay. Well, you could work that out. Okay, I'm just not going to draw it. Okay. Learn to draw these things for some variety of simple shapes and understand how those shapes come about. Although we're not going to use most of those shapes in this course, you have to understand how they work. Okay. And it's not difficult. I mean, I learned to do it in high school too. Okay. You're as smart as I am. You can do that. Especially since you've already seen it. Almost for sure. At some point. Okay. Now, where I want to go with this, though, is I don't want to do polar coordinates. Okay. I want to go into 3 dimensions. So what I want you to do is draw me r equals cosine theta z equals 3. In 3 dimensions. I don't expect miracles of 3-dimensional construction. But do your best. Not going to give you too much time on this. Okay, so you notice that this graph fits inside a unit square, right? And I recommend, especially the conic sections, putting things inside squares or asymptotic to diagonals of squares in case of hyperbolas, right? So I'm going to draw that same rectangle down here. Okay. Good. I'm in the wrong place. You got one in the wrong place. It's in the first and second clause. Let's get it. So get that, here it is. No. Draw that rectangle where it should be. I'm going to erase this and do it right. Go ahead, draw it. So I'm pretending to screw it up just to confuse you to see if you can straighten it out for me. Okay, is this what you drew? That's what I should have drawn, right? Because in order to draw correctly, turn things around a little bit. This isn't particularly well drawn. This should be on a little further, but you get the idea. Okay, it's positive x. And y goes positive, and then right. X and y axis is going to look like that. And now you can sketch it, points of tendency will be these. Kind of badly drawn, it's a little outside. There it is. Okay, now all you do is you come up to z equals 3. This is z equals 0, and you draw the same rectangle. So you can just raise this point up, raise this point up, raise this point up to here, raise this point. Kind of unfortunately close to the z-axis. Okay, so here it is, and there's kind of an auxiliary x-axis out here, but you don't really need it. You got your points of tangency. That was pretty bad, but there it is. Okay. Okay. Well, how about r equals cosine theta z from 0 to 3? There's two ways I can draw this. I can start connecting vertical lines here, and you get a pretty good picture. It'll look something like this. Okay. And then you can kind of do this. And you got a fairly decent representation. Within the limits of your artistic ability, you can kind of sum up. But I'm gonna actually, just to make a point, construct 2 more of these rectangles. And it's kind of easy to construct these rectangles because I've already got these vertical lines here on this prism. And the thing is fitting within the prism. And now I can, on my points of tangents, and repeat all the errors I made drawing the original one. And then I can start putting these lines on it, kind of shading it. And now I can pretty well see the cylinder, right? Okay. Well, what would you say the coordinates of this point are? Oops. Take the point directly above here. What are the coordinates of this point? About to turn the thing on, but okay, some of you did this in rectangular coordinates. Okay, which is pretty much okay, it's kind of what I expected. We want to relate the rectangular coordinates to the cylindrical coordinates. Okay, 1, 0, 3 in rectangular coordinates. X is 1, you know, from this picture, we know that X is 1. When I finally got this picture right, that's what I have. Okay, didn't label it, but it's clearly X equals 1 and Y is 0. Because we're on the x-axis. And then we're 3 units high, 1, 0, 3 in rectangular coordinates. Okay. Now, what I really want to write down though is polar, or actually cylindrical coordinates. Cylindrical coordinates are simple. It's one, 0, 3. Okay. Now, in cylindrical, it means okay. So in cylindrical coordinates are theta z. It's just polar coordinates down here in the XY plane. And then how high it have to go, z. So if you understand polar coordinates, well, cylindrical coordinates are really pretty easy. Now there's stuff we do with cylindrical coordinates that aren't as easy. Let's just get the scheme done, okay? So let's ask you to do another point. Let's ask you to do this point. It's above this point. And now, I marked this pretty well at the point of tangents, although it might be hard to see from there. She thought the angle was pi over 3. Okay. I can live with that, but that's probably not it. If it's the point of tangency, then what would be the line here? What's the slope of that line? Can you show me as a finger? Yeah. Okay. Now Carla's sitting there like this. So she had it. Okay, you got that? Why is it 1? Well, this is a unit square, right? What are the coordinates of this point? 1/2 this way and 1/2 this way. Okay. So that the angle here would be pi over 4. This angle is pi over 4. Okay. So here we can kind of draw that line. And label it theta equals pi over 4. And of course, now we're directly above that. So, well, what's R? R is here it is. Okay. R is going to be the cosine of pi over 4, which is the square root of 2 over 2. Okay. You can also get that from 1/2 and 1/2 like there. You get 2/4. Square root of which is 1 square root of 2. Okay. Then you gotta be version all that. Okay, so. You get that by just doing the cosine of pi over 4 once you figured out that angle. But if you don't know the angle, you can still find R if you know that that's a point of tangent. And you gotta have the geometric intuition and knowledge to know that. It doesn't go very deep, but it can go really deep. Okay. And then Z is 3. So this is okay. Straightforward though. And we can do it in rectangular coordinates. 1/2, 1/2, 3. Okay. 1/2 unit here, 1/2 unit there. You can say. All right. So we get the idea of cylindrical coordinates. Okay, so what are the cylindrical coordinates? First of all, carry it away. Polar coordinates is 1, 5, 3. We will then do the symmetrical coordinates of 5, 3, -7, but that's going to be even. Okay. How do we get polar coordinates of 5, 3? R is the square root of 5 squared plus 3 squared. It's square root of 34. About 5.87. Okay. Here's theta. Here's the right triangle. Okay. And we got 3 here and 5 here. So the theta is the arctangent of 3/5. Okay. So in general, R is the square root of x squared plus y squared, right? And theta I write it like this. The arctangent of y over x, of course, the arctangent of y over x is just between negative pi over 2 and pi over 2. We've got angles over here, right? Well, if x is negative, you add pi to the angle. So if the angle is here, the arctangent is going to give you an angle down here. It'll be a negative angle. If you add 180 degrees, which is pi, to that, you get the right angle. Okay. And work that out. The book explains it. Maybe not in the same terms, but that's the most simple way I know to write it. The arctangent doesn't give you an angle between 0 and 360 degrees. There's an angle between 90 degrees and 90 degrees, but we don't do any calculus of degrees. We never use degrees. Always use radians. Okay. So that's how you write out angles and degrees, 30.7. Don't do it anymore. avoid it if you possibly can. If you want to get the degree so you can visualize and make sure it looks right. That's fine. Okay. But that's only for visualization. You never ever use it in calculation. Okay. What are the rectangular coordinates at this point? Okay, some not quite. I didn't give you a lot of time. First of all, 3 pi over 4. That's out here. That's 45 degrees. Then we come out for you. There's the point. What are the rectangular coordinates? Well, you do a triangle here. Okay. There are 2 ways to look at this. We can actually do it this way. Here your angle is 3 pi over 4. Here's 4. Circular model tells you. X is 4 times the cosine of 3 pi over 4. Y is 4 times the sine of 3 pi over 4. Just the circular model. So that's really straightforward. Okay. So in general, now you could do this triangle and say, well, that's 45 degrees. You know, it's cosine of 45 degrees, and this time is negative square root of 2 over 2. Okay. Sine is square root of 2 over 2, multiply it by 4, and you get it. But we really don't want to think hard. We want to think simple model. In physics also, doing what is. Okay. Although that's a little ambiguous. Sometimes we use. Sometimes we don't, depending whether we're doing calculus or not. Okay, so area conversions, that's it. That's the whole definition of polar coordinates. Okay, cylindrical coordinates, just throw in Z. And there's no conversion. So in cylindrical coordinates, there it is. Okay. Okay, so it's enough about cylindrical coordinates. We need to talk about spherical coordinates, which are a little more involved, but you can kind of base it on cylindrical coordinates. I'm going to show you. It's easiest to see these coordinate systems in relation to your Cartesian coordinates. And it's interesting, incidentally, in reading this fairly rigorous development of general relativity, which is, of course, for everything else. Okay. I think it was there that the guy had a little footnote and said that spherical coordinates came before cylindrical or Cartesian coordinates. Because use spherical coordinates to navigate the sphere of the Earth. Latitude, longitude, and radius, which is constant, okay? You got to know the radius to relate it to latitude and longitude. It's very interesting. I never thought about that. I knew Descartes came up with Cartesian coordinates. But spherical coordinates predated that by a couple hundred years. Okay, so let's do cylindrical coordinates. It's fairly simple. And we've got a point out here. And just to locate it, we'll do some projection lines, okay? So we can immediately see the coordinate, the y coordinate, and the x coordinate. If we want to do cylindrical coordinates, right there is r, right? And right here is theta. And right here is z.
I will.
Okay. Well, spherical coordinates are gonna different color here. It's not moved so much as contrast with what we did before. Okay. Oh, I guess so now z is only this high. Anyhow. Got this, okay? Well, this is now our radial vector, and you see that this is convenient. If this is the center of the Earth, then every vector of this length is going to be on the surface of the Earth. And if we do all such vectors of this length, we get the whole sphere, right? So we just let this thing wiggle around all over the place until it's been everywhere, which will take a while because points don't have any dimension, but we get a sphere. Is that pretty clear? Okay, just like if we let R go through all possible angles, of course, that's all in the plane and it sweeps out a circle, right? There's Blackburn. Okay. So we call this, instead of R, the Greek letter corresponding to R is rho. Same letter we use for density in physics. Okay. Only so many letters, they all have a lot of functions. Okay, so there's rho. And theta, well, we just take this thing and project it down here. So now we got a green line right on top of a red line. And theta is the same as the cylindrical. Okay. So theta works for cylindrical, for spherical coordinates. And the only problem is, of course, if we want to know the x and y coordinates, we need r, not rho, to put together with theta. Okay, but that's easy. Theta, I'm sorry, we're going to have an angle phi. Okay. Second letter of the Greek alphabet, which starts phi, phi, pho, pho. Okay. That should know, but it's how it's pronounced. Some people pronounce it phi, which just drives me nuts, but okay, once I always heard phi. I don't know, phi might be an East Coast thing. But I was another guy I heard, I think he's educated in Wyoming. Can't see Wyoming's pronouncing it. But maybe they do. Okay, it just depends on who you listen to. Okay, so here phi, obviously that's a different letter. Phi, pi, and thumb, right? Yeah, you just said that anyhow. Okay. There's pi. It's the angle with the z-axis. Okay. So first of all, theta can go all the way from 0 to 2 pi, obviously, that's polar coordinates. Okay. Pi is the angle with the z-axis. It only goes down to pi. You don't have to go any lower than the bottom. Okay. So if rho goes all the way down here, you've got all positive and negative possibilities of z. So my question now is, you got a nice triangle here. Okay. Just looking at it from a plane perpendicular to the plane of R, the plane theta equals whatever it equals here. Okay, got the angle phi, the distance rho, and the distance r. And we're projecting down here implicitly at a right angle. Right angle there, right angle here, right angle to the plane. So where's z in this? So in terms of rho and phi, you can write the expressions for r and z, can't you? You got a triangle there. We've got to figure out where z is in that triangle, but that ought to be pretty straightforward. Okay. Well, a couple of ways you can do this. First of all, the angle phi, where does the angle phi appear in this triangle? It's up here. You know, you got parallel lines here. This is a transversal. These are alternate interior angles. And if you don't understand what I just said, look up alternate interior angles, transversals, and everything else that you're told when you look it up. Seriously. Okay. You gotta know that much, John. Okay, so I didn't read my own writing in terms of it. Looked like. Okay, so anyhow, it tells you that then very clearly R equals rho sine phi. Z equals rho cosine phi. Yeah, Z is here. Clear that this is the side opposite the angle, and this is the side adjacent to the angle. That's most basic thing about right angle trig, okay? So we have to understand that. Otherwise, this whole thing becomes very mysterious. Okay, so we can say then that we've got our conversion between cylindrical and spherical. Okay, so cylindrical to spherical. There's that, right? Now, if we want to do spherical in terms of cylindrical, it is H in spherical. Going the other way, it's pretty clear that r squared plus z squared equals rho. Rho squared. Stay right there. So rho is the square root of r squared plus z squared. Theta equals theta. And phi equals what? So our tangent of r over z. Now, there's a little bit of a problem with that. Because the arctangent can give you negative values. Okay, so you gotta adjust that a little bit. I'll let you read about that. Rectangular versus cylindrical. Versus spherical. R is rho sine phi. So here's R, which now equals. Give myself my room, did I? I've got rho sine phi written pretty small there. Probably can't read it, but we know that R equals rho sine phi. Okay. So if R equals rho sine phi, then what's X? In terms of rho, theta, and phi. What's your expression for Y? You've got a right triangle here. You know this angle, you have an expression for hypotenuse, right? So it should be very straightforward to write it down. Okay. Okay, so there's our triangle. Now I'm going to right over here. Here's R, and I have trouble with the geometric orientation here today. Yeah, we want to have X going this way, Y going this way. The triangle's actually here. Here's rho. So here's R. Which is rho sine phi. So the hypotenuse is rho sine phi. That's really not the triangle one. Excuse me. That's just done without necessarily thinking much. Yeah. I could do the yellow triangle. The red triangle is going to be a whole lot stronger. So here's the red triangle. Here's rho. Here's R. equals rho sine phi. Here's theta. Here's your x coordinate. Here's your y coordinate. Should be clear that x equals, you can write r cosine theta, which we wrote down for the cylindrical coordinates, right? But we want it in terms of rho theta and phi. So r is rho sine phi cosine theta. And y is r sine theta, but that's rho sine by sine theta. Okay. It's very simple. You understand trigonometric functions of right triangle. Just all right triangle. Okay. Well, your assignment is going to run you through a lot of different kinds of shapes that you can get. If rho is constant, you get a sphere. Assuming theta goes from 0 to pi, and pi goes from 0 to pi. Okay. So what do we know rho is? That's great. So much for that. Okay. Yeah. Okay. How would you describe the surface? Rho equals 4. Theta goes from 0 to pi over 2. And pi goes from 0 to pi over 2. Rho equals 4 means you got, at this point, the whole sphere radius 4. Restricting theta from 0 to pi over 2. Well, I mean, if you draw that, you have the first quadrant of the XY plane. In 3 dimensions, you have everything above and below this first quadrant. So you have part of the sphere that's above and below first quadrant. And then that's hard to read. I'm not even sure it's going to come through well there. I really should move that over. But this condition restricts you to the upper half plane. So each of these cuts down that sphere and leaves you with an eighth of a sphere. Okay. How about right? Theta equals pi over 4. That's your only restriction. Well, we're short on time. Give you a little time to think about it. Okay, well, here's your x-axis. Here's your z-axis. You can figure out which one's the y-axis. Okay. Here's theta equals pi over 4. The only restriction, so you can have any row. Okay. Right. Okay, above and below. Just theta equals pi over 4 line. Okay. No restriction how far you go this way or up or down. Pi can be anything you get here. Okay. Makes sense. So you'll see a bunch of other examples, a lot of interactive figures, but also really think about the trigonometry and make sure you really understand polar coordinates, because we're going to have to do a lot of stuff with the cylindrical and spherical coordinates when we get to integration. Okay. Multiple integration within those coordinate systems. It can be challenging. So get this polar coordinates stumbling block out of your way between now and then.